Okay, good. Now we're recording. All right, so I'll also send out the video for last week and this week. All right, so we're dealing with thermodynamics or condensed matter material. And whoops. All right, how about this? That works. All right. One of these ways should work. All right. So we're going to be talking about a fair amount of material this week, but it's all about energy, and in particular, the conservation of energy in thermodynamics, which is the first law of thermodynamics. So the abstract is the same as last week. We're on chapter 2 now. So can anybody tell me about energy? Not you, Steve. Anybody want to tell me what energy, heat, and work is about?
Everybody should raise their hand.
Yeah.
We talked about it about a month or two ago.
I would expect most people should know about it, but people are not saying very much.
I'm very disappointed.
Yeah, so am I. All right. So how many kinds of energy can you describe? Anybody want to tell me what kinds of energy they think there are?
So there's kinetic, thermal.
Good. What was the second one?
Thermal.
Thermal.
Potential.
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 Kinetic.
Yeah. Okay, is energy a state variable in the sense that we talked about state variables last week with state functions?
No.
Actually, that's not true. Energy is a state variable. Mechanical work and heat are neither state variables, but the sum of those, energy, is. So let's see. We talked about kinetic energy. There's various kinds of potential energy: gravitational potential, electric potential, magnetic potential, elastic energy, chemical energy, radiant energy, thermal energy. There are other types of energy. There's mass energy, food, geothermal, quantum, Hamiltonian, fission, fusion, particle, antiparticle, all kinds of things out there for energy. Energy is very important in thermodynamics, and it can be described both microscopically and macroscopically. And as I said, energy is a state variable. Can somebody from last week's presentation tell me what a state variable is? Whoever's speaking, I can't hear you. You're very, 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 very low. You'll have to turn on your volume or something. So somebody want to tell me about what a state variable is in a dynamic system?
I'll take a crack at it. One of several different quantities or that together describe the state of a system, I guess. It seems sort of tautological.
No, that is exactly it. The dynamic systems, you have a state, a list of properties that describe the system. Those states, that list of properties, can be mathematically evolved over time to give you a different state. And as you keep evolving over time, the state of the dynamical system changes. And that's what a collection of state variables and a state and a dynamical system does. Now, intuitively, unless I just said this again, the state of a system is the information that determines the nature of the system in the absence of any external forces. In short, if transients of the system have damped out, it's in equilibrium, then I'm sorry, I have to move this so I get my, there we go. All right. The collection of state variables follows the state via a mathematical model. Just repeating what I just said again. The model describes the evolution of the state vector, and the elements of the state vector are called collectively as a phase space or a state space.
Is a state then a...
So there are two big ideas. First, energy is indeed a state variable. And two, energy is conserved. So what do we mean by conservation? We've talked about this many times, and there are many sentences that people try to use to describe what the conservation of energy is. One of them is the total energy in the universe is a constant. Anybody want to give me any comments about that sentence?
I think it's controversial. Depending on, you can find some people, for example, like Sean Carroll, who would point out that there may not be a way of really defining the energy, the gravitational energy of the universe yet.
I know it's going.
Other people would disagree. I would just say that statement is controversial.
Well, the big problem with it, from my point of view, is that we can never measure the entire universe, and therefore it's a statement without meaning, not without meaning, without predictability. So in the proper sense, it's not scientific. The second statement is the total energy of an isolated system is a constant.
Okay, this is what I'll do.
Any other comments about that?
Again, by isolated, you mean it is adiabatic, there's no heat transfer.
No, I don't mean adiabatic. I mean in the sense that we talked about it in decoherence, that over time, there's absolutely no way that any mass, energy, etc., can go into the constant.
Yeah, well, adiabatic,
it's
of course, adiabatic is part of that. Adiabatic just means there's no heat transfer.
Right.
So if you say it's adiabatic, it's no work's done on it, and there's no flow of material in and out, then
Right.
the system is indeed isolated.
Okay,
But
well, there's two problems. there's two problems with this. The first is that, as we talked about in decoherence, an isolated system is virtually impossible to create, and especially in quantum systems. And
Oh,
the
the other Bob. Let's see who's on. I'll tell you.
anyway, the last sentence that people usually use is energy is neither created nor destroyed.
I just-
So we talked about the universe, the isolated system
Does she have meeting number?
may or may not
You have
be
the
able
number
to
of
be
the
just
meeting?
built for
What's
some
the
reason,
number of the meeting?
but doesn't conservation of energy apply to systems that are not isolated?
He has a number of the meeting.
That's not necessarily an implication of that sentence.
She got an invitation, tried to push it.
Lastly, the sentence that we talked about, we've never observed any energy disappear or appear in a laboratory experiment. But even if it did, if we only looked at a portion of it, it would look like it was not conserving energy. So none of these statements seem to follow a reasonable meaning of conservation of energy. So we're going to use the first law of thermodynamics to try and talk about that.
Okay, but there's Noether's theorem about symmetries and conservation laws ties the conservation of energy to the fact that time is symmetrical in all physics.
Yeah, time, translation, and variance.
Yeah, and so since we observe that invariance everywhere, we've never seen an instance where that hasn't been true. That sort of implies that therefore it works at energy is conserved at a universal level.
Well,
You don't have to measure
certainly
it.
when I mean,
the symmetry principle in action.
yeah, the symmetry is important, and physicists usually point to Noether's theorem and all of the equations that we have in physics have time reversal and I'm sorry, not time reversal, time displacement, the ability to transfer from one time to another and have the same experiment. So that implies in Noether's theorem that because of that symmetry, the energy is conserved. But that's a little abstract. So in condensed matter or thermodynamics, the internal energy of a system is a function of the state function. And the change in the internal energy is simply the final version of the energy minus the internal energy. It's important to consider the transfer of energy in systems. And in thermodynamics, we use two different names to discuss two different types of energy transfer. One is called work, and this is the mechanical energy transfer of macroscopic motion. And we usually use W to denote it, and it's the work out of the system. It is the mechanical work done by the system on the environment. So mechanical work can be generalized to electrical energy, chemical energy, all these other kinds of potential energies, etc. But for the most part, we're going to simply deal with right now, the traditional heat engine idea, which means we're using force times distance as mechanical work. And there's another type of energy transfer. This type of energy doesn't cause anything macroscopically to move. There is another, is there something I can do? All right. But there is another type of something that goes on
Tell Bob it's
in a system. And if there's parts of the system that contact with each other, because we're assuming locality, then
Bob, can I interrupt you for 1 second? I'm sorry. Kathleen has called me. She's trying to get on to the conference call or the Zoom.
okay.
I don't know what to tell her.
Well, Margaret, I just added her. Was it Margaret that called you?
Kathleen.
Kathleen.
Murray.
Kathleen Murray.
Yeah, well, she was on earlier.
Yeah.
And I don't see her right now, but I'm managing the participants and she's not asking to join. So until
How would she ask to join?
Until she
How would she ask to join?
I can't put anything in. I can't do anything for her. So
Bob, may I also make a suggestion that there's somebody talking in the background of somebody's, and it might be useful to mute.
yeah, whoever's.
I think it's Jessica. I think it's Jessica.
Jessica just muted her microphone. All right, here's Kathleen.
It was not me, but anyway, I am muting.
Okay, thank you. By the way, Jessica,
Okay,
at some point, let me talk to you
Yeah,
about.
it just came up.
Bob did it. Okay, good.
Okay. Oh, thanks a lot.
Yeah, said, Bob, maybe you want to interrupt now because I may not be able to stay for the whole presentation.
Okay, you asked a question last week about what happens with proteins. And proteins have very complex interactions with thermodynamics. In particular, the details of water interacting with proteins are extremely complex. The van der Waals forces are very important. The temperature, whether it's in supercooling, I mean, there's just a tremendous number of answers to this. But basically, there are three regions of temperature. There is a cold temperature during which either below the supercooling temperature, below that temperature, typically proteins will unfold, so they will get longer. And typically when they're above a certain temperature, above which stability stays, a similar process happens. And there's a middle region of temperature slightly below the supercooling point and considerably above that in the temperature of our bodies or so. It's all stable. And in the stable region, it will, with additional energy, additional heat and temperature, it will vibrate more, but the overall length of the protein doesn't change very much. So I looked into that, and that was what I found out about it. And I'll try to send a couple of articles and a website about that for you to follow on about.
Oh, wonderful. Thank you so much, Bob.
You're welcome. Okay, so now let me try and get rid of this. All right, we can give a law of conservation of the energy in thermodynamics, and that says that the change in the total energy is the heat energy, Q, minus the mechanical work, W. And that's the first law of thermodynamics. It took quite a long period of time to realize this was about energy. Physicists had no general idea of energy, and work was an abstract mechanical quantity, sometimes useful for calculations, but not always. Heat was thought to be an invisible fluid called caloric, and it was present in hot and cold bodies. And so if you had a hot body in contact with a cold body, the abundance of caloric in the hot body would flow to the cold body, and they'd equilibrate. And work and heat were not at all the type of thing in the 1700s and 1800s. The first person who actually understood that heat and energy were the same thing was Sir Benjamin Thompson, Count Rumford. He was an American-born British physicist and inventor, and he was actually part of the King's American Dragoons, that is the American loyalist forces during the American Revolutionary War. So he fought against us. After the end of the war, he left America and went to London, where his administrative talents were recognized. And he was appointed a full colonel and received a knighthood from George III. He was a prolific designer. He even designed warships. He later moved to Bavaria, wow, can't get my words out, and entered government service there, and was completely reorganized the army. And in 1791, he was made a count of the Holy Roman Empire. He challenged the established physical theory, that is the caloric theory, and he created a revolution in thermodynamics, but it wasn't completely accepted. So he discovered experimentally how to measure specific heat of material. And when he went to publish this material, another physicist just happened to have a Swedish physicist by the name of Johann Wilk. He published it a few months before Count Rumford's attempt to publish. But from our point of view, we're interested in frictional heat. He was working on experiments designing various kinds of cannon, and they would get a piece of brass, and then they'd get a boring tool, and they'd bore out the material in the brass cannon. And he noticed that if you took the barrel and used a blunted boring tool, he could boil water within roughly 2.5 hours from boring the brass cannon. And that supply of frictional heat that you could use continuously seemed inexhaustible, and that to him meant that the caloric system of fluids was nonsense. And he published these results comparing the specific heats of the material machined away and the one that was the same, that was creating boiling water, and they were exactly the same, so the material was the same. And so he was the first one to realize that heat was a form of energy. Now, I just said that. The next person we want to talk to is Nicolas Leonard Sadi Carnot. And he was a French mechanical engineer in the French army. And like Copernicus, he published only one book called The Reflections on the Motive Power of Fire, which he actually wrote at the age of 27. And he described the first successful theory of the maximum efficiency of heat engines. And this completely changed the discipline of thermodynamics. Now, he attracted little work during his lifetime, but once later physicists, Clausius and Kelvin, formalized the second law of thermodynamics, they realized that his example of an efficiency in a steam engine was the equivalence of work and heat. And even though he had believed the caloric theory of heat, that is, these invisible fluids, it was finally solved in the 1840s by Joule and von Mayer. And Joule was an English physicist, mathematician, a brewer, born in Lancashire, and he studied the nature of heat and discovered its relationship to mechanical work. And this led to the form of the conservation of energy that we just talked about a little earlier. And I think he was actually the first one to describe that it was the first law of thermodynamics. Anyway, the unit of energy, the joule, is named after him, and he worked with Lord Kelvin to determine the absolute temperature scale, which was later named after Kelvin, called the Kelvin degrees one. And his experiments were first published in 1843. Mayer, the other one I talked about, was a German physicist, chemist, and another founder of thermodynamics. And he stated the energy can neither be created or destroyed sentence, which we have said has some problems with it, but still partially correct. And in 1842, he described the chemical process referred now as oxidation and as the primary source of energy for any living creatures. And his achievements, as many others, were overlooked, and the priority for the discovery of the mechanical equivalent of heat was attributed to James Joule in the following year. Anyway, he also proposed that plants convert light into chemical energy. all of these physicists realized that heat and work were both forms of energy transfer. And Count Rumford's boring experiment showed mechanical friction or boring generating internal energy and heat, and it resulted in the increase in the temperature of the cannon being bored. And again, the first law of thermodynamics says that if you take a look for the energy, you have the heat input minus the mechanical work out by the system. So the left-hand side on the energy is the difference of a state variable at two different time points. Doesn't matter how you get there. The input and the output states are the only thing that matters. But the details of what goes on during the process, although unimportant to energy, is not unimportant to either heat or to mechanical work. So the right-hand side are all determined by the history of the process between the two states. And they depend on the path in the, if we have an equation of state, such as the PV plane, then if you have a particular path in that plane, each one, even though they may start at the same pressure and volume and end at the same pressure and volume, the energies at the beginning and end will be the same, but the heat and mechanical work will be different in each different path. Now, I said in general, and you can expect there's usually always some exceptions. So suppose the mechanical work over the path from state 1 to state 2 is 0. That is, you lock down every movable part of the system, you don't allow the volume to change. Then the only thing that the change in energy would give you would be heat. And since energy is a state variable, under this condition, so is the heat. So that's an exception. Similarly, if the heat is 0 over the path of the system, then no heat can be transferred in or out of the system. Then, of course, the change in energy, which is a state variable, the mechanical work also will be a state variable. So this type, by the way, this type of system where the energy over the path of the system does not enter into the system, there is no heat change. This has a special name. It's called an adiabatic process, the one that Steve mentioned too. And in this case, only the mechanical work is the energy of the system. Now, both of these two cases are very special. In general, they're not state, Q and W are not state variables. There's no specific value, but rather you need to understand exactly how the process goes as a function of time in order to calculate this. Is everything fairly, any questions so far? Because we're going to start getting into a little bit more detail.
I think I have a few questions.
Okay.
A state appears to be a slice of time as to whatever it is you're focusing upon looks like at that instant.
Well, state is a list of properties that completely describe the system.
At a moment in time.
Well, at all times. So if you are trying to understand what happens about the energy of the system, you have to know the starting point and the end point in order to know what happened to the energy in between.
Okay.
Was that clear?
Yes. However, it still sounds like you're dealing with, one instant after another instant after another instant as it changes, or,
Yeah. Well, that's the way physics works. I mean,
yes.
we find, a position and we have a calculation from whatever, whether it's gravitational or any other kind of a system, you get a prediction of how that is going to change over time. Then you measure them and you find out that in point of fact, they follow exactly the path that's predicted. And this is no different. You start at a particular point and you have a prediction on how it's going to move from place A to point B. The difference being, for state variables, you don't need to know what happened in between the 2 points. Typically, you need to understand all the, detailed information about how the process moved. But for state variables, you don't need that. You only need the beginning and ending points. Now, for things that are not state variables, like heat and mechanical work, those do need to know how they operate in between the 2 points in time. So there's a difference in the way in which the variables are connected to time. In a state variable, you only need to know the beginning and ending points. But for non-state variables, you need to know all of the details in between.
Okay. Well, of course, you're talking about need to know and then versus want to know. I mean, obviously, the knowledge exists. What you're saying is it's unnecessary to have it in this point.
Well, for state variables, that's right. But
Right.
for non-state variables, you can't do anything without understanding how the details of the process are
Yes.
over time.
And if energy, from what I gather that you're saying, and you gave a couple of exceptions here, but it sounds like energy is finite. In other words, energy, there's a given amount of energy in any given system, whether it be the universe or some small laboratory closed system. And that can change, but it doesn't disappear, and it is not created. So
Right.
if you're talking about energy such as heat working on a mechanical system, once it passes to the mechanical system, does the work, then it continues to exist in some form. Is that right? So if you have a car and the car goes, and then the energy that made the car go, there's no more fuel or whatever, and then the car stops, that energy still must exist and then go on somewhere else, right?
Well, typically what happens when you run an engine, you're exploding explosions and they
Yes.
heat up, and that your whole car will, get very hot in the area where the engine is. Now, that's the reason that you have a whole cooling system in order to dump out a lot of that heat. Otherwise, it would all melt. Just the way, Rumford found that you could, by running his boring machine, he could actually boil water. So if
But
you
Lee
have
Gale,
enough heat, it would melt.
yeah. Lee Gale, if you said the energy has to go somewhere else, that's correct.
Yeah.
It can take some other form.
Yes.
Sound waves, heat, dissipation.
Okay.
It can
Okay.
do all that, but it doesn't just disappear.
Right. And for energy, the only thing that matters is the difference in energy in physics. It doesn't matter what the absolute value
What are
is.
you up to?
You can always add a constant to any number that you calculate for energy.
I'll take a walk.
And because that's a constant, the difference will always throw away the constant. So the origin, the value at the beginning is, in a certain sense, arbitrary. You can add any constant you want to that number, and then when you get to the end, you'll have another value, and with the same constant added on, then you do the difference, because it's the change in energy that matters in physics, and so that constant doesn't matter. So the absolute value of the energy is really irrelevant. It's only the differences in energy that matter. So going back to the lecture, the heat flowing into a system is, for most types of gases, because we're primarily right now still talking about the ideal gas law, usually the heat is a constant times the change in temperature. And this constant C is called the heat capacity of the material in the system. And the units are joules per degree Kelvin. In general, heat capacity depends on the state variables, and that constant depends upon the type of material. So that's not a universal constant. It's one that depends upon how the system is put together. But for most gases, in typical pressure and volumes that we're used to talking around every day, these are a constant. And the heat capacity is very nearly constant for a wide range of state variables. The heat capacity also, as I said, depends upon how much material transfers into the system. So if you start with a small amount of material and erase it by an amount delta T, then you make twice the volume, twice the material in the area, and you try to raise it to the same change in temperature, you'll need to have twice as much heat. Just as you have twice as much material, you need twice as much heat. So there's a different version of the heat capacity called the specific heat capacity, which is the mass of the material times the heat capacity divided by the mass. So C divided by M gives you a little c. And this is a constant in joules per degree Kelvin kilogram. So you can either use heat capacity or specific heat capacity, and the name specific heat capacity is usually shortened to just specific heat. Water has many subtle and different properties for life processes, but for large-scale thermodynamic systems, water can usually be closely related for just a few constants. 1 calorie is about 4.2 joules, and the specific heat of water is 1 calorie per degree Kelvin per gram. So if we had a glass of water, say 100 grams of water, the heat would be about 400 joules per degree Kelvin. So if we have two systems which are able to transfer energy between the systems, and we suppose that these two systems are completely isolated from the outside world, the environment, there's absolutely nothing going on inside, then no heat can be exchanged with the outside environment by definition. And nothing can be done by the two systems to interact with the environment. Also, there's no, if we just have two systems sitting there with no mechanical interactions going on between the systems, the only type of energy transfer is heat. And the first law says that the system is zero. The total energy or the energy change between the 2 points will be zero. So, and the mechanical work, we've said there is no mechanical work going on, so that's zero. So we have zero equals the change in energy, which is equal to the heat minus the mechanical work, or zero. So you have two changes of energy, one heat and one mechanical work, and that's equal to the heat. So they're all heat types of change. So that one system will have a initial temperature and a final temperature, and the second part of the system will have an initial part of the initial temperature of the system and the final one. And we've always observed that when you let heat just go over time, the two systems will equilibrate. That is, the temperature will eventually be the same. So the final temperature in both cases will be the same T. And so we know that it's T minus T1, T, and T delta T2 is T minus T sub 2 initial. And we can do what's called calorimetry. This has nothing to do with the caloric theory of heat, but the use of calories in heat, which is a different measure of heat, just a different unit than joules.
Bob,
And yeah,
when you get a second, I want to go back to the previous slide. I've got a question for you.
okay. Yeah.
When at the beginning you talk about the total energy of the system is zero. We always don't we always
There's
talk
no
about the
change
change in
to be-
energy?
Pardon?
Don't we always talk about the change in energy? And we never, like you said before, you can't really talk about what energy of a system is. You can talk about the difference in energy between two instants in time, but the total energy of the system is this, right? Is
Well, we're talking about two state variables. Energy is a state variable. So the change in energy is zero.
the change, that's what I'm saying. You can say that total change in energy of the system is zero, but you
Right.
don't ever
But
talk
there is
about
another type of energy, which is heat. So the total heat must be equal to the total energy. It's got to be zero. So there's two types of energy. There's a change in temperature in the one part of the system and a change in temperature in the other part of the system. So they each have two different changes in heat, and there's a specific heat constant times the change in temperature one time plus the, plus the specific heat times the change in temperature of system two.
Right. I guess this is more of a maybe just a semantic issue, and I surely don't want to hold you up with this. But again, it was this reading this first line saying that the total energy of the system is zero. You basically want to see the change.
It should say the total change in energy of the system is zero. Should
You
say
said,
change.
Bob,
Yeah.
I just got a text from Art Salsfus. He's saying he wants you to let him back in. Somehow he's not in.
Oh, okay. Got him. All right. He's back in.
Is he back? Okay.
Well, I just admitted him. Okay. So, so yeah, we're talking about the total change in energy.
right. Good. That goes back to the very first question about, is energy a state? Because we always only talk about the change in energy.
Right. But
and you actually made the comment before that there is no absolute value for for energy.
Right. But if you take a look at, in a PVT system, pressure times volume is energy. So you can get a number by multiplying the pressure times the volume and getting the energy. And then you can do the same thing at the end of the process. And the change between the two is what the difference in energy is. So you can get a number to begin with, and you can get a number at the end and get a change that way. But those numbers can always be added a constant to, and they won't change anything.
Okay. All right. Thank you.
Sure. Okay. So calorimetry, calorimetry is the process where you can use changes in temperature, and if you know one specific heat of a material and you know the systems involved the way this one was designed, you can calculate the other specific heat simply by taking the one that you know, taking the change in part 1 and divide by part 2 and adding a negative, and you get the specific heat of the other two. So calorimetry is a way of determining specific heats for different kinds of material. So let's take a look at equation of state systems, and we'll deal with a piston, which we've talked about before. We know that there's pressure on the inside of the piston from whatever gas is inside at some temperature, and that will cause the piston to move over if you have small pressure changes, you'll get small changes in distance dx. Now force, as I just mentioned, is pressure times area. So we know that the mechanical work is the force times dx, and we know that the force is pressure times area. So the mechanical work is pressure times area times dx, but dx times the area is simply the change in volume. So the mechanical work can be simply the pressure times the small change dV. So we can look at this in a PV plane the way that we've talked about before. And we have some initial pressure and volume. And I evidently have mistyped this. It says V and V. This is P up here, sorry. So you have a process that goes through here. You have an initial pressure and volume and a final pressure and volume. Then you want to ask what's going to happen. Well, we just had it in the previous one. We said the work is the pressure times the change in volume. So if we have that same picture, And here I now have the proper P and V. Sorry about that. Anyway, here we have a small change in volume. And here we have the pressure. So pressure times the change in volume, this little rectangle is that mechanical work that's done. So the whole amount of work that's done is the area from the initial to the final under this curve. And that's written by that equation. So you just have the entire area underneath the curve, and that is how we calculate it. We integrate over the path of the pressure as a function of the volume times the change in volume. Now, if you have two different paths, then the work done on path one will be different than the work done, the mechanical work done by path two, because why is that true?
Different areas.
Different areas, they're not state variables. So if they were state variables, you'd simply need to know the beginning and ending values. You wouldn't need to know about the area. But these are not state variables, and you do need to know these, so that you're right, the area is different in the two curves. Now, we can also consider a cyclic process, one that starts at a particular pressure and volume and ends at the same one, goes around in a circle over and over and over again. So obviously the total energy change in a cycle is zero. And if that's true, that means that since that is equal to Q minus W, that means that the area under this curve, which is cyclic, is non-zero, and therefore as you go around the circle, the heat is equal to the mechanical work. So again, we've talked about an ideal gas last week and now this week, and it's a very special case, but one that's very useful. And the equation of state is pressure times volume is a constant times the temperature in degrees Kelvin. And we can have a molar specific gas constant, which is the number of moles times the specific heat, but that is simply a constant alpha times nu times r, and that number is useful. It's a scalar number, has no units, but it's but it is specific to each type of material. So for helium, alpha is about 3/2. For nitrogen, it's about 5/2. And we'll use some of these constants alpha in some of the calculations we do later. So yeah? Somebody want to have a question? Oh, they were just coughing, I guess. Anyway, suppose we have a container with a wall, and each of those two sides of that wall, which we're assuming are infinitesimally thick, have two equal volumes. Then if they're at a particular temperature T and the other side is a vacuum, we can let the wall move up and the gas will expand to the entire container, that is twice the volume. But remarkably, the temperature won't change. The system has no mechanical work done, hasn't moved anything, so W is 0, and the energy, the change in energy is 0, so the heat energy is also 0. So for a state function that would normally be on, it can be on pressure and volume, can be on volume and temperature. Pressure and temperature, we'll talk about volume and temperature. It is a constant, and that means that the state function is simply a function of the temperature. And that is a pretty amazing result. So let's consider it a isothermal path. And what does an isothermal mean? It means it's got the same temperature everywhere. So there'll be, at the beginning and the end of the process, there will be no change in temperature. So an isothermal path is also a constant energy path. So the change in energy will be 0. And again, where you simply get the same result we have always had, that the heat is equal to the mechanical work. So what happens if we consider a constant volume path in the process? So since the volume is constant, the mechanical work won't change, because you can only change something by having some force acting, and force is pressure times change in volume, and the volume is a constant, so there's no change in volume. So the mechanical work has to be 0. So we know that the specific heat is the number of moles times the specific heat constant. And we know that the heat divided by the change in temperature is equal to that, and that's a constant. So the energy is linear in the temperature. So you have a energy at T equals absolute 0, and then you have the number of moles of the material, the specific heat, and the temperature. And that's all of that goes on in an isothermal path.
Bob?
Yeah?
Yeah, let me just ask you a quick question. Are you using the convention that delta E is equal to Q plus W or Q minus W? I forget.
Q minus W.
Okay, thanks.
Sure. So let's compute the work in the expansion. We have pressure times volume is a constant times the temperature. We have an isothermal system, so temperature is constant. The work, the mechanical work, is the integral over the volume of the pressure times the volume. So the work, putting in the pressure, we take this nu times RT divided by V. Nu, R, and T are all constants. We've said this is an isothermal system. So the mechanical work is the integral from the initial volume to the final volume of the change in volume divided by the volume. And if you remember your high school calculus, that is the logarithm of the volume of the final volume divided by the initial volume. So the mechanical work done in an isothermal expansion is a constant times the difference in the logarithm of the volumes. We'll finish the work that I'm doing by taking a look at the path of an adiabatic expansion. That is, no change in the heat during the expansion. And so the curve here, you'll notice, goes quite quickly down compared to what we've seen in previous pictures. And we can, in fact, compare, this is an adiabatic change. This is an isothermal to the same volume. This is a constant volume process. So if we take a look here, we get to here by following an isothermal to here, and then a constant volume and process to get to the same place. Come on. All right. So the change in energy is because we're talking about an isothermal process. We're talking now about this portion of it. Temperature is constant. Change in energy is 0. And then we have a constant process here. So I'm sorry. Yeah. So in the adiabatic process, we have the integral of the pressure of volume times change in volume. And this is some delta energy. And we know that the energy at the beginning and the end are state variables. So if we're looking at the, at the isothermal and then constant volume, the change in energy from the beginning to the end point of the two different ways is identical because they're state variables. Now, in the appendix, this requires actually solving an ordinary differential equation. So for many of you, this is abstract art, and I've left it into the appendix. But the process says that the logarithm of the pressure plus a constant gamma, and this gamma is a function of the alpha of the material with a specific heat, times the log of the volume is a constant. And we use gamma as 1 plus alpha over alpha. And you'll see that in the appendix. And so the pressure times the volume raised to the gamma power is a constant.
The German.
Yeah. Go ahead. Who, any questions? I guess not. Okay. So the pressure times volume to the gamma power is a constant. So let's review what we've talked about. We found that physicists were confounded about the physical systems in thermodynamics and eventually discovered that heat wasn't a fluid, but energy. And the first law of thermodynamics is the conservation of energy. And it says that the energy is the internal energy, the heat, plus, well, actually, I should say minus the mechanical energy, W. This is a mistake. That's a minus. Energy is a state variable, but heat and mechanical energy are not state variables. And for non-state variables, the process is path dependent. Various forms of specific heat generally show that they're, for many, many gases especially, you can have a constant times the temperature. There's many processes that follow, and one is isothermal, a constant temperature process. Another is isobaric, a constant pressure. Adiabatic, no heat being added into the system. A cyclic system, beginning and end positions are the same. Two isolated interacting systems will only exchange heat. And we discussed calorimetry, the measurement of heat capacity, the mole specific heat of any particular material for typical pressure and volumes are simply a constant for that gas. And the area under a path measures the mechanical work. And the first law of thermodynamics is the conservation of energy. And we had important processes. Free expansion in a piston causes no change in the temperature. The mechanical work of an isothermal process for an ideal gas is a constant times the logarithm of the ratio of the volumes. And the path of an adiabatic process in an ideal gas follows pressure times volume raised to the constant gamma is also equal to a constant.
Yeah, Bob, I'd emphasize that these last results apply to an ideal gas only.
Right. Oh, absolutely. That's what I've been saying for.
Right. Okay.
Yeah. No, these are all results only for an ideal gas. But that was what that was what we focused on last time. And next week, we'll hopefully finally understand traditional entropy and statistical mechanics and develop the ideal gas law using the insights that Maxwell found in statistical mechanics. And then we'll start on Maxwell's demon, and then finally move on to what the whole reason of doing all of this, that is to understand the basis of thermodynamics on information and the fact that information is actually physical, not just some bunch of bits. So I have no idea where I am in terms of time.
11:20.
It's 11:20.
Okay.
Yeah.
So
Thank you, Bob.
questions, answers, questions, statements.
Oh, that was well done. I appreciate it.
Thank you.
Thank you.
Thank you, Bob.
If anybody is interested, and this is only peripherally related to this topic, tomorrow night I think Wednesday the 7th, and then the following week, PBS is doing a two-part of a documentary put together by Ken Burns, which is based on a book called The Gene, and it's on genetics. And I just finished reading the book, which was exceptional. And so if anybody happens to have some free time, I don't know, maybe you're all busy out running around, but if you happen to be home, I believe you can either record it or watch it, but I think it's on PBS tomorrow, 8 o'clock, and it's called The Gene. It's a two-part Ken Burns documentary. And I'm based on, if it's anything like the book, I think you'll find it quite interesting.
Great.
And when is the second part
The next
happening?
week. I think it's both Wednesdays. I think it's the 7th and the 14th. I just get a note periodically from PBS, and it was ironic because I just finished reading the book, which my son had given me a few weeks ago. I finished reading the book this weekend. And then all of a sudden it popped up that this documentary is a new release. So I think it's a new PBS documentary.
Thank you.
Yeah, thank you. I appreciate that. Where am I getting out of this?
Before you close the meeting, Bob,
Yeah?
are you going to send me an invitation for our meeting this afternoon?
Yes, I
Okay,
will.
great. Bob is giving me Zoom lessons. Or he's my Zoom consultant, let's put it that way.
Yeah, I'm not sure I can actually give lessons, but okay. Let's see. Oh, pause share. Yes. Stop share. That's what I was looking for. Okay, good. Now we're back on.
That was great.
Okay. I
It was
apologize.
good.
It just takes so much work to get this material together. I'm not able to do 2 hours worth of presentation, but I will continue to at least do an hour and a half like this. So.
Well, I think it's great, Bob. And by the way, I have 3 Zoom meetings today. I'm getting all zoomed out. You know?
Okay.
Bob, what you're doing, I think, is terrific, and it has lots of implications, including keeping us together as a group. Thank you.
Yeah.
Oh, you're welcome. I'm
Thank you.
glad. At least I no longer have to do anything with the observatory here. Normally I do lectures there, and I do stargazing, I do swoon the moon, all kinds of stuff down here, but it's all locked down because of the virus. And so I have more time available for putting these presentations together.
Arthur Karp would have been very proud of you.
Yes.
Thank you. Yeah, Art was a good friend. We would often argue, but it was not about each other. It was about various technical aspects of physics. So he just never seemed to understand in special relativity that the time dilation was about changes in reference frames, not about some gravitational or some acceleration causing a change from one place to another. And we argued about that over and over and over again. But other than that, we were usually pretty good. And
He always liked to poke, you know. He was in my philosophy class also. That's how I got into physics. The physics club, Art invited me to come, and he just was, you know, such a force. I mean, he'd always shake things up, you know. He'd always have a comment to shake things up, and it was great.
Yep.
It was great.
So
yeah.
He was, when I talked to him less than a month ago, he had been saying that his pain level was well managed, and it was just that he was tired all the time. So I hope that he didn't have pain through to the end. That always made me feel so good that he was only tired and not in pain. Anyway, we'll miss him. At least I will. All right.
Hey.
If there's no questions, I'm gonna
Can I
end.
just ask something as the last?
Sure.
Is there any way we could contribute with something to Art's family, Arthur's family? Do you have any ideas about that, anybody?
Well, I would assume, but this is my way of thinking about it, that we should, collect some money and put it into whatever charity he wanted to use. That would be the way in which I was thinking of doing. But everybody can, talk to his wife and find out about what charity he wanted to use. But that's my guess. That's simply a guess, not any information about that. We should just call.
Could we send some flowers to the family?
Yeah, that sounds like a good idea. I know a couple of good florists in Walnut Creek. I'll arrange to have a nice set of flowers sent to Art's wife.
And they could contribute, of course, monetarily to that.
Yeah, I'll send an email out about how much it's going to cost, and people can donate if they want to. It doesn't matter. I would do it on my own anyway, so it doesn't matter.
I'm not a great fan of flowers. Just from a point of view, I think Laura Lee. I know both Laura Lee and Arthur quite well, and I think she's at a point where she's got to get her life together without Arthur. And flowers have the habit of reminding you, of what just happened. But that's just an opinion on flowers.
Or anything else what she might enjoy, just cards.
Well, the thing I think anyone who wants to can just call her up. She's actually I've talked to her. We talk to her fairly often, and she's taken this very well. She knew it was going to happen for a long time, and so if you called her up and chatted with her, I'm sure she'd enjoy that. That's
good idea.
You can call her
I
up.
agree.
I will do that. Thank you.
As long as she's not overtired, having all these calls, answering, and it is hard to know how she feels about it because
I can tell you she feels okay. They both knew this was going to happen.